Now, I'm sure you thought that you were in a biology class, and therefore you wouldn't have to worry about any of this messy chemistry or physics stuff. But in reality, the sciences are far more interrelated than you might guess, and it's important for us to understand some basic principles of chemistry and physics in order to more fully understand biology. So, I ask that you bear with me as we take a short chemistry detour. For this video, I'm going to focus on these two topics, energy and matter. The energy part, fortunately, is very simple. First, though, we have to understand what exactly energy is. The textbook definition you probably got from a high school science class is this: energy is the ability to do work. Okay, fine, got that part. But what exactly is work? Well, simply put, work is the movement of matter. So, if we put it all together, energy is the ability to move something. An easier way to think about this is by using yourself as an example. When you have a ton of energy, you have a lot of ability to move, don't you? When you're tired, though, you have almost no ability to move. It's the same idea. This brings us to the first law of thermodynamics, which tells us this: energy cannot be created or destroyed, just changed. Now, the created or destroyed part is pretty simple to understand. All the energy that currently exists in the universe is all the energy there ever will be. However, it can move a bunch within that. The energy from the sun, for example, gets transferred to the oats growing in a field, which gets turned into a granola bar that gives you energy to go on a run. The energy never runs out, it just changes from place to place. The second law of thermodynamics adds on to this concept. It has to deal with entropy, which is a very fancy word to refer to this concept. Randomness will always increase. Things will always, eventually, go from a state of order to a state of chaos. We care about this in biology because it has to do with our metabolism. That food energy from the granola bar makes your metabolism work, and eventually it leaves your body as heat energy that then goes somewhere else. That going somewhere else part is an example of entropy. Now that we've got energy covered, let's talk about matter. Matter is all the stuff that exists in the universe. If it's made up of atoms, we say that it's matter. But what are atoms then? Well, they're made up of 3 smaller particles that I'm sure you've all heard of: protons, neutrons, and electrons. Protons are positively charged, electrons are negative, and as I'm sure you've guessed, neutrons are neutral. Protons and neutrons make up what we call the atom's nucleus. You're right, I forgot to say. This isn't the same nucleus that's in a cell. A nucleus just refers to a small container. Actually, it literally translates to seed or kernel. So, unfortunately, both the cell nucleus and the atomic nucleus have the same name. For this video, though, whenever I refer to a nucleus, I mean the one in an atom. This atomic nucleus is located in the center of the atom, and around it orbits the electrons. The electrons are really the ones we care most about, so I'm going to spend most of the rest of the video on these. Electrons are particularly important to biology because they can hold light energy. The energy from that granola bar earlier, the oats stored the light energy of the sun in their atom's electrons so that that energy could then be transferred to your body when you ate it. Now, before I move any further, we first have to understand what an element is. An element, like the ones you see on the periodic table, are just different types of atoms. Each one has specific chemical properties that make it unique, and this is determined by the number of protons it has. What we call the atomic number, that big number you see by an element on the periodic table, that just tells us the number of protons. Hydrogen, for example, has 1 proton, and the number of electrons is generally the same as the number of protons. Sometimes, however, they aren't the same. If the number of electrons is different from the number of protons, we call it an ion. Ions are really important in biology because they act as on and off switches. That means they can turn on or off a specific chemical reaction. A famous example of this is with calcium ions. Calcium normally has 20 protons, 20 electrons. But a calcium ion only has 18 electrons. Now, ions are named after their charge, so to figure out their charge, we have to subtract the original number of electrons by the new number. Here, we have 20 minus 18 equals 2. But we have to remember that the electrons will give a negative charge, and because we have more protons than electrons, we're going to have more of a positive charge than a negative one. So we call this calcium ion calcium 2+. These calcium 2+ ions have the ability to turn on muscle contraction. Now, I know that sounds like a lot. Students often struggle with this idea of ions, so let's do a couple practice problems together to make sure we really understand it. Let's take a look at chlorine, for example. According to its number on the periodic table, it normally has 17 electrons and 17 protons. But chloride, a chlorine ion, has 18 electrons and 17 protons. If we use our rule of subtracting the new electron number from the original, we do 17 minus 18, which gives us -1. Now, let's make sure that aligns with our charges. Chloride has more electrons than protons, so it should have more of a negative charge. That means our math is right, and therefore this ion is called chlorine -1, or its fancy chemical nickname is chloride. A famous ion that you'll be looking at a lot in biology is H+ or hydrogen ions. Hydrogen is the first element on the periodic table, and it has 1 proton and 1 electron. However, if the ion version is +1, then we know it has to have 1 more proton than electrons. Since it only has the 1 electron to begin with, then the ion version must then have 1 proton and 0 electrons. Now, we hopefully have a basic understanding of matter and energy. I know it may seem a little confusing, and you might be asking what this stuff has to do with biology, but we'll cover more of that in the next video, I promise. For now, it's just good to keep these concepts in your brain, as they'll be helpful down the road. Many scientific subjects are like this. Often you'll have to know some basic foundational concepts before we can start building the whole house. So it may look like a pile of rubble for a little bit before that begins. And for right now, you know some of the building blocks that help keep us alive.